we see calendar, we are having on 21st of this month.
Yes. So 21st, I think it will shift to I think 28 if I'm not wrong. Okay. So within that, we need to complete the syllabus. That is 1.5 module I need to complete. So I request all of your cooperation and support. So to complete this 1.5 module, I will not go in rush that I need to complete the syllabus because of the AI internals and all. But you need to cope up with me. I'm going to take some extra classes for you all people. Okay, so that the concepts will be understood from clearly from your end, so that you can perform well in your internals. Okay, so I will see how many classes additional I need to take. So I will ask some other faculties if they are ready to give some extra classes means, and I will take those extra classes, or else after 4 o'clock or Saturdays, 1 or 2 hours I may extend it. Okay.
Yeah, sure, sir.
Yeah. Okay. So let me wait for another 3 minutes and we will start the class. And I request all the students kindly ask your friends to join the class now. Okay. So shall we start the class then now, or we will wait for another 2 minutes? And yes, Pushkar, which textbook Sridhar sir was referring? Do you know anything on that?
No, sir, only he was sharing the PDF. That's
Ah,
it. So which
okay.
book it is, I don't know, sir.
Okay then. Okay. Okay, so once again, a very good morning to all the students. So today we are going to start with a Boolean algebra. So as you suggested, or as sir has been started this module number 5, so I'm going to continue with this module number 5 from the Boolean algebra. Okay. Can anybody tell me in Boolean algebra what sir has done? Means I think sir has done up to De Morgan's law, right?
Yes, sir.
Yes. Okay. So I will start with the Boolean algebra basics a little bit once again, so that it will be continuation for you people. Is that fine?
Yes, sir.
Okay. Thank you. Okay. So let me share the PDF. Whether the PDF is visible to you now?
Yes, sir, visible.
Okay.
Yes,
Thank you.
visible.
Yes. Thank you. Okay. See, since my digital writing pad is it is not working, so you please kindly bear with me for another 3 to 4 classes. So because it is gone for the repair. So once I get that digital writing pad, I will solve all the problems which is related to the Boolean algebra, everything in the digital pad only. But for the time being, around 4 to 5 classes, I will be handling only in this PDF. Okay, and if any problem has to be solved means, then I will take a white sheet and I will solve it, and they will show you how you can solve the problem. Okay, so the first thing in the linear algebra, that is nothing but in the digital transformation. So if you want to understand the digital transformation, is the first and foremost things you need to understand what is a Boolean algebra, and how, what are the problems or what are the theorems which are associated to this Boolean algebra, you need to understand. So this is the fundamental step. It is necessary for all of you to go further to understand the digital electronics in a complete manner. Okay. So this Boolean algebra, it has been started in the year 1854 by George Boole. So we call is the father of the Boolean algebra also. Okay, and he has governed some rules and laws. So with the use of these rules and laws, we can able to simplify the Boolean algebra or the algebraic expression in a easier manner, and also we can able to realize these Boolean algebra with a simple circuits, that is nothing but you already learnt about AND gate, OR gate, NOR gate, and right. So with the use of those AND gates or the basic gates, we can able to realize the Boolean expressions. So if you have a complex Boolean expressions means, then if you want to implement, or we say that if you want to practically implement that Boolean expression means, then you need large number of basic gates. So in order to avoid those large number of basic gates implementation, so what the Boolean algebra, it says that you can minimize the number of gates through the use of this Boolean laws. So how best you can make use of this Boolean law, so that you can reduce the maximum amount of gates when you go for the realizations. So it will facilitate, or it will help all you people to solve the linear algebra in an efficient way, and it will simplify your circuit so that you can implement them with the basic gates with a less number of basic gates. Okay, so in order to understand this Boolean algebra theorem, so we will be using some parameters. So the first parameter we are going to call it as a variable. So what do you mean by variable? Variable is nothing but it is a temporary entity which you are going to use in order to represent the Boolean algebra. Okay, so variable is nothing but it is a symbol, or it is a temporary entity which we are going to use for an arbitrary element representation. So in the digital notation, or in the Boolean algebra, we will be having only two values, either 0 or 1, since we are mainly talking about the binary. So the variable, it may take 0 or 1, since we don't know which value it will take. So we want to generalize that expression. So in order to generalize the expressions, so we will be using a variables. So for the notations, we will be using a alphabets. So through the use of alphabets, we can create a variables. So if you do not know what exactly the variable will take the value, so then you can generalize them and we can represent in terms of variable. The next thing what we are going to use it, we are going to use the constants. So the constant value in the digital field, or in the digital notation, we will be using only two values, that is 1 or 0. And you can see here in the given expression, so what you have, so you have a y is equal to a plus 1 you have. So y is equal to a plus 1. So a is a variable. So we don't know what exact the value is holding the a. But you can see plus 1 is there. So the plus 1 is a constant. So this we call it as a constant expression. So means what? The expression which holds a constant variable, we call it as a constant. So in the Boolean algebra, we will be using only two constant, that is nothing but 1 or 0. Okay, so one more important parameter what we will be using in a Boolean algebra is the complement variable. Okay, a complement variable is nothing but it is a negation of a variable. It is a negation of a variable. So let's say if you have a variable is a, means let's say if you have a variable a is, then the complement of a variable you are going to represent it with a bar. Okay, so you are going to represent it the a bar. So if you are holding a value a is 1 means, then a bar will be holding a value is equal to 1. So means what? The complement of a variable, we are going to call it, either we are going to represent it with the a bar, or sometimes we are going to represent this complement with the a dash also. Okay, so a dash means it is a complement of a variable. Okay, And the next thing what we are going to use is that is a literal. So literal is nothing but so the whenever at each occurrence of a variable in a Boolean function, either in an complement or an uncomplement form, is called as a literal. So in the expression, so if an variable or if an complement of a variable, if it appears in the expression means, then we call it as a literal. Okay. And one more last, what do you mean by Boolean function? A Boolean function is nothing but it is a combination of your variables, it is a combination of your complement, it is a combination of your constants. We call it as a Boolean expressions. So if you have a three variables, then you are going to represent these Boolean variables in terms of expressions. Okay, so let's say one of the simple expression or a Boolean expression how we can write is that is nothing but if a Boolean function it is dependent on three variable, so you are depending on three important variables. So what are those variables? So the variables is a, b, c. So you're going to write f of a comma b comma c, and for which expression it is holding, so how it is behaving, this function how it is behaving, or what is the relation among the variables. The relation among the variables in this expression, it is nothing but a plus b bar into c. And one more expressions you have, it is nothing but f is equal to, or we can represent like this also, or we can represent like this also, the Boolean function. So that is nothing but f is equal to ab plus bc plus c. So means what? A Boolean expression is represented by f. It is a combination of your variables. Anything. It may be a plus b, or it may be a plus b plus 2. Anything. It is a combination of variables or literal constants. We call it as a Boolean functions. Okay, so these are the some of the basic terms what you need to understand. So before we go for the actual realization of the Boolean algebra equations. So we have studied variable, constants. Complement means negation of a particular variable, we call it as a complement. Literal is the appearance of a variable in the expression, we call it as a literal. And Boolean function is it is a combination or constitutions of the variable constants with some relations, we call it as a Boolean functions. Is that clear, this one? Is that clear, this one?
Yes, sir.
Okay,
Yes,
so okay. See, these are the basics things for you people. If it is very basics means you can tell me, sir, we have known already this means you can go ahead means, then I will go ahead to the next section. Or else whatever the little basics things I need to explain for you people, I will explain, I will go to the next section. Okay. The next one we call it as a Boolean laws. So we have a Boolean laws. So the first law we call it as a AND law. So this AND law, it is called as a multiplication law. It is represented with a symbol called as dot. It is represented with a symbol called as dot. So you can see if two variables are having a relationship called as AND means, then we are going to represent that is nothing but y is equal to a and b. And is the relationship between a and b. So we are going to represent in a symbolized manner, that is nothing but y is equal to a into b, multiplication a into b. So that into symbol we are going to represent in a digital notation or in Boolean expression with a dot. Okay, and you can see here in the given expression y is equal to a and b. So y is the output variable, input variables are a and b. And for that, what is how this y variable is output you are getting based upon the input variable, we have written the truth table. So truth table is nothing but the relationship between the input and output, we are going to call it as a truth table. So this is the expression. But how this expression, so if I substitute some values over there means, then I will be getting what are the possible output of y for the corresponding inputs I have noted down over here. Okay, so I have taken two variables. So what are those a variables I have taken is a and b variables I have taken, and different combinations of these a and b variables I have used, and for that what is the corresponding output I am writing out in the table. So this table we are going to call it as a truth table. It will give you the relation of the output variable which corresponds to the input variables. So you can see here y is equal to a and b. So now I am substituting the value. So when a is equal to 0, b is equal to 0, what is the output y? 0 into 0. So we know that in algebra, Boolean algebra, 0 into 0 is 0. So therefore you got the output is equal to 0. Next, I am changing, means different combinations of I am changing when a is 0 and b is 1. So 0 into 1. So in the Boolean algebra, what is the value? 0 into 1 means the value is 0 only. Next, 1 into 0. So 1 into 0 means again it is a reverse combination of this only. So therefore the answer is equal to 0. Whereas the first case, when a is equal to 1 and b is equal to 1, you are going to get output is equal to 1. So therefore the y is holding the value 1. So you can see here in the AND operation, when both A and B are 1 logic high, then only you'll be getting the output high. Otherwise, for rest of the cases, your output will be low only. Is that clear?
Yes, sir.
The sir has done this already.
Yes, sir.
Sir
Yes,
has
sir.
done. Okay, we'll just quickly move on to this. Okay. Next, OR law. So OR law, we are going to represent it with a addition symbol or a plus symbol. So similarly, you can see here A or B. So I think you have gone through that sets. So in the when you're solving the sets examples, so you'll be using A or B, A and B like that. No. So OR operation means we are going to represent with a plus symbol. So the corresponding truth table we have noted down over here is, so you can see here the output, the y will take a value 1 when any one of the variable is logic high, means then the output will be high only. So when a and b is equal, when either in a or b it is 1, the output will be 1. When a is 1, b is equal to 0, output is 1. When a and b are 1, the output is 1. Okay, so this we call it as a OR law. The next one we call it as a NOT, or it is also called as a complement. It is also called as a complement. So you can see here we have two notations are there for the complement. A is equal to y bar and a is equal to y dash. So both are same. So complement, as I said, negation of a particular variable, we call it as a complement. So when a is 0 means, then y will be, if y is equal to a bar means, so if y is equal to a bar means, then your output y will be 1. When a is equal to 1, the output will be 0. Okay, and these are some of the special cases what we are going to consider in the case of this Boolean loss. So you can see in the AND operation, any variable if you multiply with a 0, the output will be 0. Any variable if you multiply with 1, the answer will be whatever variable you have taken, that answer only you will be getting. When you multiply the same two variables, you will be getting the same variable, that is you will not get a square, since in digital you have only 0 or 1, so you will be not getting a square, they will be getting a only, and a into a bar you will be getting the answer is equal to 0. So these are the some of the special cases what we are going to consider in the case of AND operation. Similarly, OR operations, you can see here a plus 0 you'll be getting a, means for any variable if you add 0, so that original content of the variable will not change, so therefore you'll be getting a only. And a plus 1, see you can see this is very important. So when you're solving the Boolean expressions, we will be using this expression regularly. A plus 1, see when you add any, so one, let's say a is taking a value called as 0, a is taking value called as 0, so 0 plus 1 1, so you got 1 only. Now when a is equal to 1, so 1 plus 1, so you'll be getting 1 only. So means what, when you add 1 to any variable, the result will be 1 only. Similarly, a plus a, you'll be getting a only, and a plus a bar, you'll be getting always 1. So means what, we know that in ORing operation, any one variable has to be 1. So since a plus a bar, so any one variable will always be 1. So therefore, this expression will hold a value is equal to 1. And for the NOT operations, you can see here, a, when you take double bar, means when you take the complement of complement, you'll be getting the original variable. Okay, and when you take 3 times the complement of the variable, you will be getting the negation of the variable. When you take 4 times complement of the variable, you will be getting the original variable only. So what it suggests is that, so if you take even number of complement of the given variable, you'll be getting the original number only. If you take or odd number of complement means you'll be getting the negated version of the symbol you'll be getting. Okay, so these are the special symbols for special cases what we will be taking in the solving the Boolean expressions. So if you have noted down means then it's good. If you do not have this information means I request all the students kindly make a note of this and we will go ahead for the next concept. So I will share this PDF, okay? Since for 1 or 2 classes I will not share it. So after that I will share you this PDFs. So you can go through this before I take the classes. So if you can able to understand means it's good, or else again we will means I will take the same PDF and I will explain you so that it will be clear for you. Shall we go next?
Yes, sir.
Oh. Yes, the next one we call the laws of Boolean algebra. So there are three basic Boolean algebra laws are there. So as you already know, so what are those? Commutative law, associative law, and a distributive law. Okay, so this part we will take it later. So first you mainly concentrate on these three laws. So what are those laws? First one is commutative law. So what is this commutative law? Says that if you add two variables, that is a plus b, if you change their positions then the result will remain same only. So you can see here a plus b which is equal to b plus a. So for that we have written a truth table over here, and for that we have written a truth table over here. So you can see here a plus b, 0 plus 0, 0 will be 0 plus 1, you'll be getting 1, 1 plus 0, you'll be getting 1, and 1 plus 1, you'll be getting 1. Similarly, if you change the position, means if you write first b and then a means, then the answer is remain same. So means what? The Boolean expression holds good the commutative law. So since a plus b is equal to b plus a, so therefore we can say that the Boolean expression holds good the commutative law, or we can say that Boolean expression satisfies the commutative law. Okay, so means what? If you change the variables, that will not be applicable, or it will not alter the result. Similarly, for the ANDing operations also it is same. The commutative law holds good for the AND operation. So you can see here a and b, if you change the position of the variables, the result is equal to the same when you change, when it is ab and when it is ba, the answer is equal to c. So we can say that the commutative law holds good for the multiplication operator. Commutative law holds good for multiplication operator. Have you known this already?
Yes,
Yes.
sir.
Next. The next one we call it as a associative law. So what is this associative law? Is said that, so you can see here, if you ORing the several variable and the result if you adding with one more variable means, then it does not affect if you change the position of the ORing of the variable. So here what we are trying to do is, first we are ORing, that is first we are adding b plus c and then we are adding with a. So it holds good when you do the same operations, when you add a plus b variable and then later if you add c, then it does not affect for your resultant. So means what? Associative law holds good for the ORing operation or a OR operations. So similarly for the AND operation. So you can see first a and b multiplication I have done and then I am multiplied with the c. So the result will be same when you can multiply b and c and you or and with a. Okay, so means what? Both OR operation and AND operation will holds good for the associative law. Okay, and finally the distributive law. So what is this distributive law? Says that A into B plus C, it is nothing but A into B plus A into C. So you can see what we should do is, so we should multiply with A into B and we should multiply A into C. In between you have a plus sign, so the plus sign we have represent like this. Okay, so what happens? A into B plus A into C. So this is the distributive law. So what it says is that ORing the several variables and adding the result with a single variable is equivalent to adding the resultant with a single variables with each of the several variables and then ORing the product. So you can see first what you are doing is ORing the several variable, the result you are multiplying, the result you are multiplying or adding, which is nothing but adding the resultant variable, that is the first variable, with the several variables, and the result of them, if you ORing, the result will remain same. So this is what we are going to use it in a Boolean expression, or it is called as a distributive law. So your distributive law, associative law, and the cumulative law all holds good for the OR operation and the AND operations. Okay. So the next. So these are some of the identities of the Boolean algebra what we are going to use. Okay. So the first we call it as a identity law. So why it is called as the identity law is, see, when you and any value or when you or any variable with 1, you'll be getting the same element only. So means what? When you do any operation with a particular element or particular value, if you're getting the result as the same original variable, means then we call it as an identity element. So in the AND form, the identity element we call it as a 1. So that is nothing but 1 into A is equal to 1. So the identity element is equal to 1 in the case of AND form. Whereas in the case of OR form, the identity element is 0. So if you add 0 for any variable, you will be getting A only. So therefore we say OR, that is 0 is an identity element for the OR form. So in the AND form, the identity element is 1, whereas in the OR form, the identity element is 0. So this we call it as an identity law. So why it is called as identity? Because we are taking this AND in the case of AND operation, that is 1 in the case of AND form and 0 in the case of OR form. So if you do any operation with any element, if you getting if the resultant element is same as the original, means then we call it as an identity of that element. Okay. So the second one is we call it as a null law. So what is this null law means? If you do some operation, if the resultant is equal to 0, means then that operand we are going to call it as a null operand. So in the multiplication, 0 is a null operand. So why? Because when you multiply 0 with any one of the variable, the result you are going to get it as 0 only. But whereas in the case of OR form, when you but in the case of OR form, what happens is, so even you can see here, when you, if A is equal to 0, so if you do 1 plus A, you will be getting 1. So initially the output the A was holding 0, but the output what you are getting is 1. So means what? The complement of the value you are getting. So therefore we say 1 is a null law for the OR form and 0 is the null law for the AND form. Okay, so this we call it as a null law. So in the case of AND form, it is A into 0 into A is equal to 0, whereas 1 plus A is equal to 1 you are going to get. Okay, so the next one is idempotent law. Okay, so this law what it says is, when you multiply the same element with the corresponding element, the result you will be getting the same only, or the original element only. So here you can see A into A is equal to A only you will be getting, or A plus A you will be getting A only. The next one is inverse law. Okay, so for each element, so if you multiply or if you add the complement of that variable, means then we call it as a inverse law. So you can see here in the AND form, A into A bar you'll be getting 0 and A plus A bar you'll be getting as 1. So this we call it as a inverse law. Okay, so when you take the element, if you do the operation AND operation with the complement of that variable, means then we call it as an inverse law. You can see A into A bar you'll be getting 0 and A plus A bar you'll be getting as 1. Okay, so and the commutative law. So what is the commutative law? You just now we have studied, that is nothing but A into B is nothing but B into A. In the case of OR, it is A plus B is equal to B plus A. Associative law, A into B into C is nothing but A B into C. Similarly, the distributive law and the one more important, two important laws what we are going to use is the absorption law. So you can see the absorption law. What is this? A into A plus B is nothing but A, or else in the case of ORing form, A plus A into B, it is nothing but A. And the one of the important De Morgan's law, what it says is A into B, it is nothing but A plus B bar, or A plus B whole bar, it is nothing but A into B. Okay, so A plus B whole bar, it is nothing but A bar into B bar. So this is nothing but it is A bar into B bar, A bar into B bar. Okay, so this is the De Morgan's law what we are going to use in the case of simplification. So this is very powerful law what you are going to use in the case of realization of the basic gates. So I request all the students kindly make a note of these identities so that it will be helpful for you to solve the problem. Are you able to understanding what I am telling?
Yes, sir.
Yes, sir.
Yes, whether sir has already done this identities?
No, sir.
No, right? Okay. I request all the students kindly make a note of this. Kindly make a note of this. So you should tell me once it is over. Okay, because otherwise I will not get whether you have completed or not. So you can see here A into B plus C is nothing but A into B plus B into C. So this is B into C. And this is A bar into B bar. So what this De Morgan's law says is that, so you can alter the expression without changing the resultant. How? By changing. So you can see here how, by see each wherever you have a and operation you replace with or operation, wherever you have a and operation you replace with or operation, and you should take the complement of them, complement of individual elements you need to take. If you have a and means you need to replace with or, and the complement of each element you need to take. Similarly, you can see over here. So what we have done is, so we have replaced A plus B, bar is there. So what we have done is, so the and or operation has been replaced with and operation, and you have taken the complement of them, means the complement of individual elements we have taken. So this we call it as a De Morgan's law. Is that clear?
Yes, sir.
Whether it is completed? Have you taken these identities?
Yes, sir.
Okay. So we will prove whether it is true or not. So for the first thing, what we are going to do is we will prove it whether this distributive law holds good or not. Okay. So what we should do is either we should take left hand side and we should prove it to right hand side, or we can take right hand side expression and we can prove it to the LHS. Okay. So therefore I have taken the right hand side expression. So what I have done is, so I have taken this right hand side expression. So now what we should do is, so you can see here, the first element I will multiply with the remaining two element, and I will take the second element, I will multiply with the remaining element. The remaining thing I will not alter it. So now first what I will be taking is, I will take a into a. So that is what I have written. Next, plus is there. So I wrote plus. So first this element they have taken plus. So now what they have done is a into b. So what they have got, a into b. Next, what is there? Plus is there. Now what they have done is a into, that is c into a. So they have written a into c. Next, c into b they have written. So they have written b into c. Okay, so if you take this element, or if you take this element, it will not alter. So whatever they have taken is, they have taken this element a into a, they have written. Next, a into b, they have written. Plus is there. So this plus they have written. Next, what they have taken is, this say they have taken c into a, they have written ac. Next, they have taken c into b, they have written bc. Okay, so now you look at the idioms, or you look at the identities what we have drawn. So what the identity we have drawn? So you can see here a into a. So what is the answer? A into a. So that is what they have replaced it over here. Next, AB they have kept it as it is. Next, AC they have kept it as it is, and BC they have kept it as it is. Is that clear?
Yes, sir.
Yes, sir.
Okay. Okay. So now what they have done it over here is, in this entire three terms, they are taken a as a common. So this entire expression, they have taken a as a common. So in this three elements, they have taken a as a common. So when you take a as a common, what you have left? You have left with 1 and ab. So you have taken a, so you have left with b, and here you have taken a, you have left with c. Okay, so you have left. So now you see here, so what is this? 1 plus b plus c, 1 plus b plus c. So now what idioms we can apply for this? Can anybody tell me what idioms we can apply for this? So let's say, let b plus c. So b plus c is the right. So let's say we will call it some other variable. So let b plus c is the right. So we will call it as d. So now you can see this expression, what is that? It is 1 plus d. 1 plus d. Now what is the output of this 1 plus d? Can anybody tell me?
Sir, 1.
Yes, very good. Why? Because you can see here 1 plus a. The answer is 1. 1 plus a, the answer is 1. You can see here 1 plus d, the answer will be 1 only. So therefore the entire expression, so this entire expression, so whatever you are writing, right, so this will give you, the answer is 1. So 1 into a, you got it as a, and bc I have written as it is. Now you can see here the left hand expression and this expression both are same or not. Whether it is correct?
Yes, sir.
Did you understood this one?
Yes, sir.
Okay. Similarly, one more, there is absorption law. We want to verify it. So what is the absorption law? It says that is nothing but we have taken this. So you can see here a into a plus b is equal to a. So you are supposed to get a into a plus b is equal to a. You need to get. So since we can simplify this expression left hand side, so I have taken left hand side and I will verify whether you are going to get A or not. So you have taken here A into A plus B taken. Now what I will do, I will multiply. What is that? A into A plus A into B. So that is what we have written. A into A plus A into B. Now you see here A into A. So what is the output of this A into A? You will be getting, what is the resultant of A into A?
A.
Yes, A only. You will be getting A only. Why? Because you can see here A into A, you will be getting A only plus AB. I have kept it as it is. Now, what is the common among these two? The common among these two is A. So I have taken is A as a common. So when you take A as a common, so what you have left? You have left with 1 plus AB. So in AB you have taken A, you have left with B. Now can anybody tell me what is the output of this 1 plus B?
1, sir.
1. Why?
One.
Because, yes, very good. 1 plus A or 1 plus B, you can see here it is a null law. So with the use of null law, we can write it is 1. So now 1 into A, you'll be getting A only. Is that clear? So means what? So when you solve any Boolean expressions, so these laws will help you, or these identities will help you to directly substitute, so that your simplification will be easier. So therefore, it is necessary for all the students, you need to remember them. So when you see, when they give you the problem to simplify the Boolean expression means, then with the use of these laws, you can simplify easily. Understood?
Yes, sir.
Next one. So we will see what is more on this De Morgan's law. So what is this De Morgan's law? So what it says, you can see here, A plus B whole bar can be written as A bar into B bar, or A and B whole bar can be written as A bar plus B bar. So what it says, says that, so you can see here, any logical binary expressions remains unchanged. Any logical binary expressions remains unchanged when changing the all the variables to their complement, changing the all the variables to their complements. So I have changed B to B bar. Next, changing all and operations to or operations, changing and operations to or operation, changing all or operations to and operations. So changing all or operations to and operations, or else take the complement of their entire expression. So when you take the complement of the entire expression also, it will not change. So this is the De Morgan's law. It says, even though you can think it is very simple law, but it is very effective law when you want to simplify the Boolean expressions. So what we will do is, first we will verify this, and then we will see that whether it is holds good or not. Once we can verify, and then we can say that yes, it holds good. So for in order to verify this law, so we have written a truth table. So what is the truth table we have written is, we have written a truth table for two variables A and B. So when I take two variables, the maximum combinations you'll be getting only these. Okay, so you can ask me, so why we have written only this means, when you take only two variables, so you can see here 2 power 2. So what is the value of 2 power 2? You'll be getting 4 only. So you'll be getting 4 different combinations. So all those combinations we have taken. So we are realizing this expression. So you can see here. So what we have taken, A I have written, B and I have written. Now I want to write the complement of that. So when you write the complement A, what will A bar you'll be getting? 1, 1, 0, 0. So that is what the complement of A I have written. Next, B bar complement, what you'll be getting? 1, 0, 1, 0 you'll be getting. So 1, 0, 1, 0 you'll be getting. Next, what you need? A into B you need, A plus B you need. Okay. So that is why what I will do is A into B whole bar, I will make it note of it, and I will be having A plus B whole bar. Okay. So A into B. So first what you do is you do A into B. So what is A into B? So let's say right over here. So A into B you write over here initially. So 0 into 0, the answer is 0. 0 into 1, the answer is 0. Next, 1 into 0, the answer is 0. Next 1 into 1, the answer is 1. Now for this what you should do is you should do the complement of this. So when you take the complement of this is what they have written. 0 will become 1, 0 will become 1, 0 will become 1 and 1 will become 0. So therefore AB complement they have written it over here. Okay, so this is how we have written AB bar, AB bar. Next, what you need? You need a plus a bar plus b bar you need. So I have written a bar plus b bar. So what is a bar plus b bar? You need to OR them. You need to sum them. 1 plus 1, 1. 1 plus 0, 1. 0 plus 1, 1. 0 plus 0, 0. Okay, so this. Now what do you need? A plus b whole bar you need. A plus b whole bar you need. So first what you should do is you should take down what is a plus b. What is a plus b? Can anybody tell me? What is a plus b?
It is 0.
0, 1, 1, 1. Isn't it? A plus b. 0 plus 0, 0. 0 plus 1, 1. 1 plus 0, 1. 1 plus 1, 1. So when you take the complement of this entire thing, so what you'll be getting? You'll be getting this answer. So 0 will become 1 and the remaining all 1 will become 0. So this is what you'll be getting. Is that clear? Is that clear?
Yes, sir.
Okay.
Yes, sir.
Next, yes. Now what you want? You want A and B. Means A bar you need and B bar you need. Anyway, I have A bar and B bar, so I will multiply. So 1 into 1, 1. Next, 1 into 0, 0. 0 into 1, 0. Next, 0 into 0, 0. Okay, so from this table, now you verify whether you are satisfying the De Morgan's law or not. Okay, so what is this De Morgan's law? You can see what is the left hand side you have. The left hand side you have A plus B bar. So A plus B whole bar is there. So this I need to verify with which A bar into B bar. A bar into B bar. Now what is the output you can see here? 1 0 0 1 0 0. So means what? De Morgan's law holds good. For this entity or for this law, it holds good. Similarly, you take down this. What is this? A bar B is nothing but A bar plus B bar. So A B bar is nothing but A bar plus B bar. So what is the answer you can see here? 1 1 1 0 1 1 1 0. So this element or this law also holds good. Is that clear?
Yes, sir.
Okay, so I think it is time up. So the remaining thing, that is the digital circuits, I will take it on in the next class. Okay, and see if I am going very slow means so this is the first one class. I'm not aware how speed you can able to grasp the things. So that is why I went very slow. And these are the very basics. I think you will be remembering or you will be knowing this. And as the days progress, we will speed up our understanding level. Is that clear? Is that clear?
Yes, sir.
Yes, sir.
Yes, yes.
Okay. Okay. So I quickly take up the attendance. I request all the students, please answer your attendance. Just wait a minute. Nitish. Nitish, is number 63. I request all the students kindly attend your answer your attendance. Nitish. Kevin. Kevin.
Present, sir.
Kishore.
Present, sir.
Krupa. Krutika. Krutika. Yes. Krutika, yes.
Present, sir.
Kumar. Kumar. Okay. Sai Shrujana.
Present, sir.
Sundar.
Present, sir.
Kusuma, yes.
Present, sir.
Praveen. Likita. Rahul. Please answer your attendance.
Present, sir.
Rahul is present. Okay. Lisha. Lisha is here.
Present, sir.
Kavya.
Present, sir.
Indra.
Present, sir.
Manasa. KV.
Present, sir.
Manasa
Present,
V.
sir.
Okay. Manasa V.
Present, sir.
Sandeep. Sandeep Yadav. Manish.
Yeah, present, sir.
Manoj. K.
Present, sir.
Manoj SR.
ಸರ್ ನಮಸ್ಕಾರ
Namaste.
ಸರ್ ಆರು ಗೌರ್ಮೆಂಟ್
Yes, Manish. I request you to mute yourself, Manish. Manish. Okay.
Yes, sir.
Meghana.
Manish Kumar, sir.
Okay. Meghana.
Present, sir.
Muhammad Akram. Amin.
Present, sir.
Mohan.
Present, sir.
Mohit.
Present, sir.
Monica.
Present, sir.
Monica G.
Present, sir.
Monica M.
Present, sir.
Monisha.
Present, sir.
Rasul.
Present, sir.
Mukul Yadav.
Present, sir.
Kaushik.
Present, sir.
Kaushik. Okay. Navyashree.
Present, sir.
Okay. Navyashree, yesterday you were absent.
Yes, sir.
Okay. Naveen KR.
Yes, sir.
Naveen Kumar.
Present, sir.
Neetu.
Present, sir.
Nihal.
Present, sir.
Nikhil Kumar. Nikhil Kumar. Nishant Gowda. Sorry, Nishant. Nishant. Please answer your attendance. Nischita. Nischita BK.
Present, sir.
Nitin.
Present, sir.
Nitin MS.
Present, sir.
Nivedita. Nivedita. Please answer your attendance, Nivedita. Okay. Nikhil. Nukula Nikhil. Absent. Okay. Shashi Rekha.
Present, sir.
Pooja R.
Present, sir.
Pooja V.
Present, sir.
Prajwal KP.
Present, sir.
Prajwal R.
Present, sir.
Varu.
Present, sir.
Prajwal. Sorry, Pranjal Srivatsav. Pranjal Srivatsav. Okay. Pratham Kumar.
Present, sir.
Preeti.
Present, sir.
Pushkar Ranjan.
Present, sir.
Okay. Pushpa. Arpita.
Present, sir.
Nirul. Nirup, sorry.
Sir.
Rahul.
Present, sir.
Okay. 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 Yes. Anyone I have missed out means you can tell me. I will note it down.
Sir, Krupa present.
I is present.
Akram.
What is
Akram.
Rupa? Yes, tell
Pranav and
me.
Akram. Pranav and Akram.
What is US number, Pranav?
115.
Pranav, present. I have made it present. Yes. One more. Okay. Next, anybody I have missed out? Okay. So thank you everyone for attending the classes. Okay. So we will see the remaining sections or the concepts in the next class. Okay. So thank you all.
Thank
Thank you,
you,
sir.
sir.
Okay. Thank you.